Stars are not scattered randomly through empty space. They are born in their thousands in the coldest and densest corners of the interstellar medium. Between the stars of a galaxy lies a thin, turbulent sea of gas and dust, and most of it, the hot plasma, the warm neutral hydrogen, is far too tenuous ever to collapse. Only one phase is cold and dense enough to fall under its own gravity, the giant molecular clouds, the great stellar nurseries. This chapter follows the chain of physics that turns a cold, formless cloud into a blazing star from the vast scale of the cloud, through the instability that dooms it to collapse, down to the newborn protostar and the disk of planets forming around it. A giant molecular cloud is a genuinely enormous object, holding anywhere from 10,000 to 1,000,000 times the mass of the Sun, spanning tens of light years, and yet astonishingly cold, only 10 or 20 degrees above absolute zero. Its hydrogen is locked up as molecules rather than single atoms, which is what gives it its name. But molecular hydrogen is nearly invisible, radiating almost nothing at these frigid temperatures, so astronomers trace the gas instead by the glow of the carbon monoxide mixed within it. And the dust, barely 1% of the mass, dominates everything, absorbing starlight and re-emitting it in the infrared, so that the earliest embedded phases of a star's birth are hidden from ordinary telescopes and revealed only in the infrared and the submillimeter. These clouds are not smooth, quiet balls of gas. They are shot through with a hierarchical tangle of filaments and clumps, sculpted by a fierce interplay of supersonic turbulence, magnetic fields, self-gravity, and the feedback of stars already born within them. The gas churns at speeds far above its own whisper-quiet sound speed, and magnetic fields thread every part of it. The iconic images of these nurseries, the Eagle Nebula's pillars of creation, the glowing sword of Orion, the cosmic cliffs of Carina captured by the James Webb telescope show exactly this. Great columns of dark, dense gas being lit up and eroded by the ferocious ultraviolet radiation of the massive stars the cloud has already made. The extreme cold of these clouds is not incidental. It is the very thing that makes star formation possible. The gas is heated gently by cosmic rays and by starlight striking dust grains, but it is cooled far more efficiently by the radiation of trace molecules, which carry heat away as infrared light that escapes into space. The balance settles at a frigid 10 to 20 degrees, hundreds of times colder than the warm gas around it. And this matters enormously because, as we are about to see, the mass of gas that can collapse under gravity scales steeply with temperature. The very coldness of a molecular cloud is precisely what allows lumps of merely stellar mass to become gravitationally unstable and begin to fall. Any theory of how stars form must reckon with the turbulence. In 1981, Richard Larson identified a set of scaling relations that still anchor the field. Larger clouds contain faster internal motions. The clouds sit close to the balance between their gravity and their kinetic energy, and their surface density is roughly constant. Those internal motions are supersonic, the signature of a turbulent cascade, and the modern understanding is that turbulence plays a dual, almost paradoxical role. On the largest scales it acts like a pressure, holding the cloud up and keeping star formation slow and inefficient, but on small scales the very same turbulence slams gas together in shocks, creating the dense knots that go on to collapse. Star formation is graviturbulent. Gravity and turbulence are not simply enemies, but collaborators. So when exactly does a lump of gas collapse? The classical answer is the Jeans instability, worked out by James Jeans in 1902. Imagine a small ripple of extra density in a uniform gas. Two forces contend, the gas's own pressure, which tries to smooth the ripple back out as a sound wave, and gravity, which tries to pull the extra material together. For a small ripple, pressure wins and it merely oscillates harmlessly. But above a certain critical size, the Jeans length, gravity wins, and the ripple grows without limit. It collapses. The mass contained within that critical scale is the Jeans mass, and it captures the whole competition in a single number. The Jeans mass has a beautifully simple form. It grows with the temperature of the gas and shrinks as the gas gets denser. Put in the real numbers for a cold molecular cloud core, 10 degrees, 1,000 molecules per cubic centimeter, and the Jeans mass comes out at around 2 suns. That rough coincidence that the natural collapse mass of cold cloud gas is about 1 solar mass is one deep reason stars have the masses they do, and it has a further consequence. As a cloud collapses and grows denser while staying cold, its Jeans mass keeps falling, so ever smaller pockets within it become unstable in their own right. A single collapsing cloud therefore does not form one giant object, it shatters into many separate cores. This is fragmentation, and it is why stars are born in clusters, not alone. There is a second, more intuitive way to reach the same threshold, through energy. A cloud is bound and prone to collapse when its gravitational pull outweighs the thermal motion of its particles, when it is either too massive or too cold to hold itself up. This reproduces exactly the same scaling, collapse mass rising, with temperature falling with density, and it makes starkly clear why stars form in the cold molecular phase and essentially never in warm atomic gas. Warm the same, gas up to 100 degrees, and its gene's mass leaps up some 30-fold, far too large to collapse. Coldness is the enabling condition of star birth. Genes imagined an infinite, uniform gas, but real cloud cores are finite blobs, squeezed by the pressure of their surroundings. The more realistic model is the Bonnor-Ebert sphere, a ball of cold gas held in a delicate balance between its own gravity and the pressure pressing in from outside. The mathematics reveals a critical mass, a maximum weight the sphere can bear and still remain in equilibrium. Load it any heavier and no stable balance exists at all, collapse becomes inevitable. There is a lovely real example in a small dark globule called Barnard 68, a starless core whose measured density profile matches a near-critical Bonnor-Ebert sphere almost perfectly. A textbook made real in the sky. Pressure is not the only thing holding gravity at bay. Magnetic fields thread these clouds, and because the gas is faintly ionized, it is tied to the field lines and dragged along with them. If a core carries too much magnetic flux for its mass, the field can, in principle, hold it up forever. But this raises a genuine puzzle. If a cloud kept all of its magnetic field while shrinking to stellar density, that field would end up thousands of times stronger than any star actually possesses, so flux must somehow be shed during collapse. In the classical picture, the neutral gas slowly slips through the ions and the field they are tied to, a process called ambipolar diffusion, gradually draining inward until the core finally tips over into dynamic collapse. Whether real cores are mostly held up this way, or mostly overwhelmed by turbulence and gravity, is still actively debated. Once a core exceeds its critical mass, gravity wins outright and the gas begins to fall inward. The clock that governs this is the free-fall time, the time it would take a pressureless ball of gas to collapse to a point, and it depends only on the density. The denser the gas, the faster it falls. A modest core collapses in a few 100,000 years, a dense clump in as little as 10,000, and the collapse is lopsided. Because the center is densest, it has the shortest free-fall time and collapses first and fastest, so the density grows ever more sharply peaked toward the middle. Collapse proceeds in a memorable phrase from the inside out. The classic description of this is Frank Shu's model of inside-out collapse, published in 1977. Once a tiny point mass forms at the very center, a wave of collapse ripples outward at the speed of sound. Gas inside the wave is already raining down onto the growing protostar, while gas outside it hangs, for now almost still. A clean and famous prediction falls out: the rate at which mass pours onto the new star is constant in time, and set only by the temperature of the gas. For a 10-degree core, that works out to about 1.5 millionths of a solar mass per year, enough to assemble a whole sun in roughly 600,000 years. Real cores are messier, turbulent, magnetized, spinning, so the true accretion is more fitful, but that elegant analytic prediction remains the field's touchstone. A subtle thermal switch governs how far fragmentation can go. As long as the collapsing gas can radiate its heat away, it stays cold, the gene's mass keeps shrinking, and fragmentation continues down to ever smaller scales. But once the central density climbs high enough, the gas turns opaque to its own radiation. The heat is suddenly trapped, the temperature shoots up, and pressure abruptly halts the collapse, forming a tiny pressure-supported kernel at the center. At this instant, fragmentation stops, which is precisely why stars do not form arbitrarily small. The smallest fragment this opacity limit allows is a few hundredths to a few tenths of a solar mass, tantalizingly close to both the most common stellar mass and the threshold for hydrogen burning. Here the microscopic physics of dust opacity reaches all the way up to help set the masses of stars. There is one more obstacle, and it is the most severe of all: rotation. Every collapsing core spins, even if only slightly, and it carries far more angular momentum than a star can possibly hold. If that spin were simply conserved as the gas fell inward, the material would whirl faster and faster and reach a centrifugal standstill long before it ever approached stellar size, and accretion would grind to a halt. Nature solves this in two ways: by redistributing angular momentum within a disk and by carrying it away entirely through magnetic outflows. The gas, unable to fall straight in, instead settles into a flattened, spinning disk, its material sweeping around the young star in very nearly circular orbits. For the star to keep growing, matter in that disk must spiral inward, and to do so, it must hand its angular momentum outward to the gas beyond it. This requires friction, an effective viscosity, and here lies a problem. The ordinary molecular viscosity of the gas is far too feeble to matter. The transport must instead be driven by turbulence, conventionally captured in a single efficiency number that astronomers simply call alpha. The question then becomes, what stirs the disk into turbulence in the first place? The leading answer is a beautiful piece of physics called the magnetorotational instability, worked out by Balbus and Hawley in 1991. Picture two blobs of gas in the disk, joined by a magnetic field line like two masses linked by a spring. The inner blob orbits faster, the field line tugs it back so it loses angular momentum and drops to a lower orbit, while the outer blob is pulled forward, gains momentum and drifts outward. The gap between them widens, the tension grows, and the whole arrangement runs away into vigorous magnetic turbulence that ferries angular momentum outward exactly as needed. Yet there is a wrinkle. The cold outer reaches of these disks are so weakly ionized that the instability may switch off there, in vast dead zones, and recent measurements find these disks far calmer than the theory predicts, reviving the idea that magnetized winds, rather than internal turbulence, do much of the real work. Those magnetized winds complete the picture in spectacular fashion. Young stars are seen, almost universally, to fire narrow bipolar jets and broad molecular outflows along their axes launched from the inner disk. They carry away angular momentum and fling some of the infalling gas back out. And the disk that survives all, this is not merely leftover debris, it is the birthplace of worlds. The very same flattened, rotating structure that solves the star's angular momentum problem becomes the protoplanetary disk in which dust grains collide and stick and slowly build the planets. Star formation and planet formation are quite literally two acts of a single play. How do we watch any of this when it is all buried in dust? Protostars are classified not by direct sight, but by the shape of their infrared glow, by how much cold dust surrounds the central object, and that shape traces out an evolutionary sequence in 4 stages. It is one of the neatest classification schemes in all of astronomy, turning an invisible, embedded process into a readable timeline written in infrared light. A Class 0 protostar is the very youngest, perhaps only 10,000 years old, so deeply swaddled in its cold envelope that the central object cannot be seen at all, and nearly all its light emerges in the submillimeter. Its defining feature is startling. There is still more mass in the surrounding envelope than in the star itself. The star is, quite literally, still mostly waiting to be built, and this is the phase of most furious accretion. A Class 1 object 10 times older has passed much of its envelope down onto the disk and star, but remains embedded, glimpsed now in the near-infrared through the cavities that its own jets have carved. By the Class 2 stage, we have a classical T-Tauri star, an optically visible young star, its envelope gone, encircled by a flat protoplanetary disk. This is the great planet-forming phase, lasting a few million years, and its light shows a normal stellar surface plus a telltale infrared excess from the disk. Finally, at Class 3, the disk has largely dispersed. The infrared excess fades to almost nothing, leaving a nearly bare young star, quietly contracting toward adulthood. In these 4 steps, from an invisible cold lump to a naked young star, the entire hidden drama of stellar birth is laid bare. But the young star is not yet a true star. As it contracts, it shines brilliantly, in fact, but its light comes from the release of gravitational energy as it shrinks, not from nuclear fusion. On the great diagram of stellar life, these pre-main sequence stars descend along characteristic tracks, cool and luminous, contracting and heating as they go. The transformation into a genuine star happens only at the very end, when the core temperature finally climbs to some 10 million degrees and hydrogen fusion ignites. That fusion generates enough pressure to halt the contraction at last, and the star settles into the long, stable, hydrogen-burning adulthood of the main sequence, the state in which our own sun has lived for 4.5 billion years. Not every collapsing lump makes it across that threshold. Below about 8% of the sun's mass, roughly 80 times the mass of Jupiter, an object can never squeeze its core hot enough to sustain hydrogen fusion. These are the brown dwarfs, the failed stars, which glow faintly for a while and then slowly fade, held up not by fusion, but by the quantum pressure of their densely packed electrons. Below about 13 Jupiter masses, even the brief burning of deuterium ceases, and by convention that marks the blurry boundary between a brown dwarf and a giant planet. Star formation, it turns out, has a firm floor as well as its towering ceiling. When a nursery finally converts its gas into stars, it does not make a single mass but a whole spectrum of them, from feeble brown dwarfs to blazing giants 100 times the Sun. The distribution of those birth masses is called the initial mass function, and it is one of the most consequential curves in all of astrophysics. Through it flow the integrated light, the color, the chemical output, and the explosive feedback of every population of stars, so that cosmology, galaxy evolution, and the chemical enrichment of the entire universe all inherit whatever is written into this one function. The foundation was laid by Edwin Salpeter in 1955. Counting the stars around the Sun, he found that above about one solar mass their numbers fall off as a steep power of the mass, the famous Salpeter slope. The steepness means the low-mass stars vastly outnumber the high-mass ones. For every 10 solar mass giant, there are a couple of hundred Sun-like stars. Later surveys reaching down to the faintest objects showed the curve flattening, and then turning over below about half a solar mass, peaking near a few tenths. So the most common stars in the galaxy by far are the dim red dwarfs, and yet the rare, massive minority produce most of the light and forge most of the heavy elements. Why the initial mass function takes the form it does, and what sets that characteristic mass of a few tenths of a sun, is one of the great open questions of the field. The leading idea connects it back to the fragmentation of turbulent clouds. The distribution of prestellar core masses, which observations find looks remarkably like the stellar mass function, but shifted higher, as though each core turns roughly a third of its mass into a star and loses the rest to outflows, and a deeper puzzle looms behind it. Is the mass function truly universal? To a good approximation it looks the same everywhere we can measure it, which is why astronomers assume it so freely. But there are tantalizing hints that in the most extreme galaxies it may tilt, with enormous consequences for the stellar masses we infer across cosmic time. Seen as a whole, star formation is strikingly inefficient. If molecular clouds simply collapsed as fast as gravity allowed, our galaxy would blaze through its gas in a few million years. Instead, it converts only about 1% of a cloud's gas into stars per free-fall time. The throttle is feedback. The first massive stars to form flood their birth cloud with radiation, winds, and eventually supernova, heating and blowing apart the very gas that made them. Much of this physics was hidden behind dust until recently, but the James Webb Telescope now resolves deeply embedded protostars and their jets, and the Great ALMA Array maps the rings and gaps of planet-forming disks down to the scale of our own solar system. Star formation stands today as a mature science built on firm foundations, genes, SHU, the initial mass function, and a vigorous contested frontier, which is exactly what makes it one of the liveliest corners of all modern astrophysics.